So this is problem number 7.15, and it states that a long solenoid with radius A and n turns per unit length carries a time-dependent current I in the phi direction. Find the electric field and with the magnitude and direction at a distance s from the axis both inside and outside the solenoid. We have this solenoid and there's has some n number of turns per unit length with the radius a. This solenoid has radius a, and we are asked to find the electric field inside and outside the solenoid. So En and E out. Inside the solenoid we have the magnetic field. We know mu naught n I in the z direction when s is less than s. This is the circle. We have the radius as s and s is less than a, the original radius of the solenoid, which is a, so it is less than a. Then we need to find out the flux B dot dA. Then B is equal to mu naught Ni, and area of this loop is pi s square because it has radius s. Further, we know the EMF, the Faraday's law, E dot dl, which is equal to minus d phi divided by dt, and E dot dl, which is equal to minus d divided by dt. We know this flux. And further, E, the circumference of this circle is 2 pi s minus mu naught n pi s square di divided by dt. Because the current is changing, all the remaining things are constant, so di divided by dt, and this En, which is equal to mu naught n pi s square divided by 2 pi s, pi will cancel, s will cancel with s. And this is the final result. This is the magnitude, and the direction of I is equal to phi. Then it means that the electric field direction will also remains in the I direction. So this is the n side. And similarly, we have considered a loop with radius s, which outside the solenoid. Then B is equal to 0 for s is greater than, in this case, s is greater than a, because this is a and this is s, so s is greater than a. But B is not equal to 0 when we have a radius s, radius a. S is equal to a. Then phi, which is equal to B dot a, and B is equal to mu naught Ni, the magnetic field of the solenoid. And area, we will consider the area of which has radius a, then pi a square. And using the Faraday's law, E dot dl, which is equal to minus d pi divided by dt, E 2 pi s, because we are considering this loop, and 2 pi s, which is equal to minus d pi divided by dt, putting the value of phi, and after some mathematical calculation, E out, which is equal to this, and this will also has the direction phi because di divided by dt. So this is the magnitude and this is the direction. So this is problem number 7.16, and it states that an alternating current I is equal to I naught cosine omega t flows down a long straight wire. We have a long straight wire and returns along a coaxial conducting tube of radius a. This is a coaxial tube with radius a. Then in what direction does the induced electric field point? Radial, circumferential, or longitudinal? The second point is, assuming that the field goes to 0 as s tends to infinity, then find the electric field. The solution is, if we have a long straight wire and it carries a current I in this direction. Then the electric field will be in this direction, but the magnetic field will be in circumferential. So it is very easy. The magnetic field will be circumferential and the electric field will be longitudinal. The second point is find the electric field E. Then if we find out the electric field E, then we use this kind of figure. We have a coaxial shape and conducting tube with radius A. Then if we consider here a loop, a square loop here, and then using the Faraday's law, which is equal to minus d pi divided by dt, and further we can also write down the Faraday's law, E dot dl, which is equal to minus d pi divided by dt, and phi we can have integration of B dot dm. Using E, which is this, and if we consider a length, which I have considered this length L, then this will be the length of this loop, which is equal to L, which is equal to minus d divided by dt. And here the integration is from S to A. We have from this is S and this is A. The integration, well, we have to take the integration from S to A. And here we have considered a small stick which has a radius S prime and the current is IDS prime. Then the magnetic field in this loop, using the Ampere's law, you can find out very easily the magnetic field mu naught I divided by 2 pi S prime. This stick we have considered, and LDS prime, this is the area of this stick, the blue stick we have considered. And then E dot dl, which is equal to minus mu naught 2 pi L di divided by dt, and the integration is from S to A 1 over S prime ds prime. And if we do the integration, then we will have log of S prime limit S to A. This is very simple. And here then E into L, and L will cancel with each other, and then we have I, which is equal to I naught cosine omega t, and they'll use putting the value limits, then log of A minus log of S, and do the derivative. Then the derivative we will have I naught is constant, then this will be minus sine omega t, and the integration of this angle with we will have omega, then minus minus will cancel with each other, and mu naught omega I naught 2 pi sine omega t log of A divided by S. We can write this in this form, log of A divided by S. This is the rule of the log, and this is in the z direction. So this is the complete problem 7.60. This is problem number 7.17, and a long solenoid of radius A carrying n turns per unit length in a loop by a wire with resistance R as shown. This is the diagram, and this is the resistance. And the first point is, if the current in the solenoid is increasing at a constant rate, what current flows in the loop and which way? Okay, here the solution is we need to calculate the current I naught. Then from Faraday's law, E, the EMF, which is equal to minus d phi divided by dt, and phi, which is equal to B dot dA, and B is the magnetic field and the solenoid, which is equal to mu naught Ni, and phi, which is the area, then pi a square. Then E, which is equal to minus mu naught n pi a square di divided by dt. All these things are constant. And di divided by dt. And di divided by dt, and the here it has been shown, it is given that di divided by dt, which is equal to k, some constant k, then this is equal to this. And from Ohm's law, E, which is equal to I naught R, and I naught, which is equal to this, and putting the value of E here, then we have I naught, which is equal to this. Since B increasing to the right and E to the left, then current is counterclockwise direction. So current flow through the resistance towards right. The current will flow to the right direction. The second part of this problem stated if the current I in the solenoid is constant, this is a solenoid and the current is constant, but the solenoid pulled out of the loop and re-inserted in opposite direction. If this solenoid is pulled in this direction and then inserted, then what total charge passed through the resistance? What total charge passed through this resistance? So we are asked to find the charge in this resistor, and dq we need to find. Now when this solenoid is pulled and then inserted, then the flux will change. Then what will be the flux? The flux will change d pi, which is equal to pi 2 minus pi 1. The flux, this is the flux, pi a square mu naught Ni, that already we know about this, and minus, and this minus, this is in the opposite direction. Then minus minus plus, and this will 2 pi a square mu naught Ni. This is the flux, the change, the flux change in this system. We also know that I is equal to dq divided by dt, and I, which is equal to E divided by R. This is the Ohm's law. And we also know E, which is equal to minus d pi divided by dt. Then this equation 1 and 2, if we compare these two, because this is I and this is I, and if we compare these two equations, then dq divided by dt, which is equal to minus 1 over r d pi divided by dt, dt will cancel with dt, and then dq, which is equal to minus 1 over r, and d phi we have already calculated, putting value, and this dq, which is equal to 1 over r, 2 pi a square mu naught Ni. So this is the total charge passed through this resistor. In problem number 7.18, a square loop, we have a square loop like this with side A and resistance R lies a distance S. This lies with a distance S from an infinite straight wire that carries current I. This is a wire which carries a current I, so that I, now someone cuts the wire so that I drops to 0. If someone cuts this wire, then the current will drop to 0, and then in what direction does the induced current in the loop? We have to find out the current, the direction of the current in this loop, and what total charge passes a given point in the loop. So first of all, we look for the current direction, and then for the charge in this loop, I have written this. And the current, if the current drops, if we cut, if someone cut this wire, then the current drops, then changing in the magnetic field occur if we cut this, because this wire which has own magnetic field, and when this current is flowing, the magnetic field around this loop which is also passing through this loop, and whenever we cut this, then gradually the current drops in this wire, then the magnetic field also changing. Then changing in the magnetic field occur in this loop, due to which induced EMF is generated in the loop. We know that whenever the magnetic field is changing, then induced EMF is generated. So this is the case here. Whenever we cut the wire, then changing the current drops, the current will change, and the magnetic field also change. Then what will happen? We can get the EMF is generated in the loop, and at the center of the loop, the magnetic field will, the own magnetic field generated in the this loop, when the induced EMF is generated, then the magnetic field will show in this direction. Then if the magnetic field show in this direction, it means that the magnetic field show this direction, then the current will flow in this direction. So it means that the current will flow in the counterclockwise direction. The current will flow in this direction. This is in the anti-clockwise direction, because the magnetic field will be in outside, and then the current will flow in this direction. Okay, the second part is we need to calculate the Q, the charge in this loop. Then first of all, we want to calculate the phi which is equal to B dot A, but the limit is from S to S plus A. And here we also consider some stick line which is at a distance S prime, and the small width is ds prime. Then the integration is from S to S plus A, because this S and this is also involved. So S and S plus A. The magnetic field in this loop, which is equal to mu naught I 2 pi S prime, if we have this stick, the blue one, then this is from this wire is at a distance S prime, and the area of this will be equal to A ds prime. Then it is very simple to integrate, because mu naught I 2 pi and A is constant, and the integration is over S prime, then log of S prime, this with this, and take the integration and then putting the limits, then we will have this will be the phi, and further we know E is equal to I loop in the loop, I in the loop, and R, and this further equal to, because current in the loop is equal to dq divided by dt, R, this is equation number first, and we also know that from Faraday's law, the EMF which is equal to minus dy divided by dt, comparing 1 and 2, then we will have, if we compare this, then dq r divided by minus d pi divided by dt. Then dq divided by dt, which is equal to minus 1 over r d phi divided by dt, putting the value of phi, which we have calculated. This is the value, and dq divided by dt, and then differentiate di divided by dt will cancel with this dt, and finally dq, which is equal to this. It is very simple. After this, integrating both sides, then dq and di and all the other thing remains constant. Then q, which is equal to minus 1 over r mu naught a divided by 2 pi log of s plus a divided by a and I. So this will be the charge in this loop. In problem 7.19, we have a toroidal coil. This is a toroidal coil with radius A and internal radius as W, and it has a height h. Then in this problem, we are asked to find the electric field at some point Z. At some point, for example, at this point Z, we need to find out the electric field. Then first, the magnetic field B inside or outside the toroid. What will be the magnetic field inside and outside? Then we will have using the Ampere's law, and the Ampere's law state that B dot dA, which is equal to mu naught n turn. We have now n turns, then I have multiplied n. And for any Amperian loop which some radius s, then B 2 pi s, which is equal to mu naught ni, and B is equal to mu naught ni divided by 2 pi s. This is inside the solenoid. The magnetic field inside the solenoid will be equal to this, and the magnetic field outside the solenoid will be equal to 0. Now we find to calculate the flux. Then the flux, which is equal to B dot dA, B we already have an inside, and dA is the area, HDS with some area, H is the height and ds is the some width of the Amperian loop. Then we must integrate this from a to a plus w, because this is the inner radius, and this is the total radius, and this is the inner radius of the solenoid. So we must calculate this from a to a plus w, and this is from a to a plus w mu naught ni divided by 2 pi hds, and all the things are constant. These are the constant, and this is the integration. And the integration is very simple: a plus w divided by a. We take this term, and I have right hand this, and this is approximately equal to w divided by s. Then w divided by a. Then w divided by a is here, and finally if I differentiate d phi divided by dt, then here di divided by dt and di divided by dt, which is equal to k, and the problem we have kept. So d pi divided by dt is this thing. Now the electric field is the same as the magnetic field of a circular current. We use this equation 5.11, where the magnetic field has been calculated already, and the magnetic field, which is equal to mu naught I divided by 2 a square divided by a square plus z square 3 divided by 2 z direction. Then this magnetic field remains the same of the electric field, which is the same as the magnetic field. Then E will be equal to this, and here this is equation number first, and here we need to calculate I, and I is unknown, using equation 7.19 state the Faraday's law, E dot dl, which is equal to minus dy divided by dt, and E dot dl, which is equal to mu naught I, and mu naught I, which is equal to this, and for this we calculate I, which is equal to minus 1 over mu naught d phi divided by dt, and putting the value of I. This is I, which is equal to this, and d phi divided by dt we already have calculated, and putting the value of d phi divided by dt and this I, then I, which is equal to minus 1 over mu naught will cancel out, and we have I, which is equal to minus n h cut omega or w k divided by 2 pi a, putting this value in equation number first, and this will be the electric field, the required result of this problem. Problem number 7.20 state that we have two loops. One is the back loop and the other one is the small loop. The back loop has radius b and the small loop has radius a, and it is at some distance far away from this. These two loops are from some distance, is shown in this figure. Then suppose the first point is, suppose current I flows in the back loop. If the current flows in this back loop, find the flux through the small loop. This is the point. Then in this case, we have to calculate the flux through the small loop. If the current is flowing in the back loop, we have to find the flux in this. Then the magnetic field at a small loop due to a large loop S. This is from equation 5.41. The magnetic field has already been calculated. B is equal to mu naught I divided by 2, B square divided by B square plus C square 3 divided by 2, and then the flux is equal to phi, which is equal to B dot A. B we have, and area of this loop pi A square, and then multiply, we have the flux. This is the flux through the small loop. The second part of this problem, 7.20 state that suppose current I flows in the small loop, find the flux through the back loop. If current is flowing in this, find the flux in this. So as the small loop can be treated as a magnetic dipole, this has been this point has been cleared in the statement of this problem. So field at a big loop due to small loop, this will be equal to mu naught 4 pi m divided by this, and this is already calculated in this equation 5.88, where m, which is equal to I pi a square, this is the magnetic dipole moment, hence the flux through the back loop. The flux through the back loop must be equal to B dot dA. B as the flux, B as the magnetic field, we will put here, and dA is the area. Now we have two parts, this part and this part, and this the unit vector r, this is the unit vector theta. Then we will provide the integration to both these two terms, 2 cos theta r and dAr, and this. Then this term will goes to 0 because the dot product is perpendicular. Then this term will goes to 0 and we will have only this term 2 cos theta and dA. This is theta, and where dA, the area for the spherical coordinate dA, we must write this r square sine theta d theta and d phi, then 2 cos theta r square sine theta d theta and d phi, and further we have to calculate this equation. Further, phi, which is equal to mu naught I a square divided by 4I, and then we have two integration. One integration is theta and the other with phi. So from 0 to theta naught, this is a theta naught, the angle theta naught, and the other one is phi, which is the rotation 0 to 2 pi. Then we will apply this separately, the integration 0 to theta naught this, and 0 to 2 pi. 2 pi, this is become 2 pi, and 0 to theta naught cos theta sine theta d pi, and sine theta 2 sine theta cos theta is equal to cos 2 theta. Then it means that sine theta cos theta, which is equal to cosine 2 theta divided by 2. So we will have a 2 here, 0 to theta naught cosine 2 theta, integration of this we will get minus cosine 2 theta. This is not a square, but this is cosine 2 theta divided by 2, 0 to theta naught, and then we will have this, and further 1 minus cosine 2 theta naught, this is actually equal to 2 sine square theta naught, because 1 minus sine 2 theta, which is equal to 2 sine square theta. Further, we also know that from this figure, sine theta is the perpendicular divided by hypotenuse. This is the perpendicular, B is the perpendicular, and this is the hypotenuse. Then sine theta naught, which is equal to B divided by R, putting the value of sine theta, then B divided by R whole square, and further we multiply some mathematical steps, and we have already mu naught pi I a square b square divided by 2r with, what is r? This triangle, from this is r, this is b, and this is z. Then from this triangle, r square, which is equal to b square plus z square, and r, which is equal to b square plus z square under root, and if we put the value of r, then this is cube, then it must be equal to 3 divided by 2, and this result and the first result that we have calculated for section A, this remains the same. This result and this A remains the same. Thank you. Last section of this problem states that find the mutual inductances and confirm that M12, which is equal to M21. This is very simple, because phi 1, which is equal to M1 to I2, and I2, which is equal to I, then M12, which is equal to phi 1 divided by I2. Putting the value of phi 1 we already calculated in section A, and this is equal to mu naught pi r a square b square I divided by this I will cancel with this, so we will get this. Similarly, phi 2, which is equal to M21 I1, and from this M21, which is equal to phi 2 I1, and putting the flux phi 2 from the previous section B, and I will cancel out, then we will get the result, and from this we can see that M12, which is equal to M21.